Hello and welcome. In this video, I'll be working through the solutions for the second part of the Unit 7 test review. So having a formula sheet or potentially a unit circle somewhere nearby may be helpful as we work through some of these, but I'll also be verbalizing what identities or what angles I might be referencing as I work through, but just thought I'd at least tell you what you might want to have ready to go. So press pause if you don't have those, grab them, and then resume afterwards. So without further ado, let's go ahead and start jumping into some of these problems. So the first few, as you can see from the standard here, involve the inverse trig functions. So arcsine, arccosine, arctangent are going to be the main three that we'll deal with. Keep in mind with each of them, I have specific ranges of possible answers that I can get. Arccosine for this first example is one that would exist in just the top two quadrants, so it would fall in between 0 and pi, or 0 and 180 degrees, depending on how I want to answer. So this one specifically says degrees, so it just needs to be an answer that falls in between 0 and 180. Now this ratio is a positive ratio, so as we can see here, that's a positive ratio inside, so now it would just be where does that ratio happen to exist on the unit circle? Well, the rad 2 over 2 for an x value should be in the first quadrant since it's positive, and it should be the one in the middle, and in degrees that would be a 45-degree angle. So that would be essentially everything we need to do for that specific one. If I would have had a negative inside, then I would have looked over into the second quadrant, at least for this specific function. So again, key part with this type of question is just being aware of what are my possible quadrants that I might need to look, and then make sure that we're also answering in the correct format, whether it's degree or radian. For number 2, if I scroll down for that one, so number 2, pretty much the same approach. Kind of need to think in terms of what does the arctangent have for restrictions. So this one actually is, if we think of the original graph, it needs to be in quadrant 1 or quadrant 4, but I also need to think of the quadrant 4 as negative angles. So again, it's somewhere in between these two spots. Now this specific ratio here we can see is a negative ratio, so that means it's definitely not going to be in the first quadrant, so it must be one of these in the fourth quadrant. So if I now utilize a unit circle reference here, the negative rad 3 angle is the one that's a little steeper in that fourth quadrant. But again, instead of me picturing it as what would be 300 degrees on our unit circle, we need to picture it as the negative angle. So if I go down that amount, that should actually be a negative 60 degrees. So my answer here is negative 60 degrees, or had this changed and slightly been different by saying what if it was in radians, I would have answered as negative pi thirds instead of negative 60. But again, this one did want us specifically in degrees, so that's what I would go with. Numbers 3 and 4 here, as you can see, just want us to basically demonstrate that we know how to utilize the calculator for these. So these ones should be about as straightforward as possible, but the key difference here is, notice number 3 is going to want our answer in radians, whereas number 4 is going to want our answer in degrees. So paying attention to what mode we're in is going to be key, at least for these two specific problems. So if I go ahead and just maybe model with a calculator here, first one wants us to do the arcsine of 0.3125. So I need to make sure I'm in radian mode for this one. So bring up a calculator, double check it says radian, so could go into not math but the mode. Double check that radian's highlighted, which it is. Quit back out to the main screen, and now it's just going to be the arcsine of that decimal, 0.3215. Close off the parenthesis. I guess it doesn't necessarily matter. I close that off, but I get this ratio now of 0.3273. So back here on the main one, 0.32, what was it, 73. If I look at the next one, or just scroll down really quick to do that one, may as well knock out both of these at the same time. This time I want to do the arc cosine, of 0.6894. This time in degrees though, so I'll have to go back into my mode, go down to where it's got degree. Just make sure that's highlighted. Notice at the top it did change to now degree. Quit back out. Do the arc cosine this time, and I already forgot the ratio, 0.6894. 0.6894. And again, press enter on that, and it gives me 46.4174-ish. degrees. So what did this say? Round to 4 decimal places, so 46.4174. And again, this time it's in degrees, so just being mindful of our notation, adding on that degrees symbol. Moving on now to number 5, a little bit more complex here. Now we got some compositions going on. So with this one, I would probably best recommend, since these aren't necessarily inverse functions, the arcsine won't cancel the cosine, is to just think in terms of what is this ratio going to be, and then worry about doing the arcsine afterwards. So I'm going to go ahead and just keep the arcsine of whatever this will turn into, and then now it's just a reference to the unit circle. So 4 pi thirds is the steeper one in the third quadrant, so if we need to help picture like what would that point really be, it should be this point down here at -1/2 comma negative rad 3 over 2. So the cosine of that would be the x value, -1/2, and at this point now it would be what is the arcsine of that. Well, which sine value has a sine value, or sorry, yeah, which angle has a sine value of -1/2? Well, again, with the arcsine, I'm only allowed to be in the first and fourth quadrant, so somewhere over on this side. This has a negative ratio, so that kind of tells me it's for sure going to be here in the fourth quadrant. And so now if I just think in terms of, okay, sine is the y value, I need it to be just -1/2. That in theory should be one that's not very far down, so that's actually going to be this angle here, and it was in radians to start, so in this case again we need to think of this as a negative angle. The negative angle that would be should be a negative, and it's the smallest of the 3 options, which happens to be a -pi6. So again, this would be -pi6 or -30 degrees if I was able to answer in degrees, but again, because this was radians, right, that's why I'm going to go ahead and make sure I just answer in radians. It doesn't really make a lot of sense to change the way that we're measuring angles. If it already started in one unit, why would I change to a different one? So hopefully that makes sense. But again, the tricky part of this one is the arcsine only giving us answers between negative pi halves and positive pi halves. And that angle originally, 4 pi thirds, was actually not even in the correct quadrant, so I did have to do this kind of more as like references. In this case, the negative ratio told us for sure it was going to be in the fourth, and now it was just picture which one has that specific value. If we move on to now number 6, notice it's similar in approach. It still is a composition. This time actually it will be slightly easier just because the outer function this time is just a trig function. So final answer for this is just going to be a ratio, so I really won't even need to worry about is this a degree or radian type answer. So anyway, kind of similar approach to the last one. I would start with what's inside, so start with that and just simplify it. So the tangent part's going to stay unchanged for the moment. The arcsine of rad 3 over 2 should give me an angle, since that's positive from the first quadrant. And so what angle I want to go with, I can answer in degrees or radians, but which one has a y value of rad 3 over 2? Well, that's the bigger one, or the steeper one in that quadrant, which is 60 degrees. Try and draw a little visual for that. Again, the y value should be larger, so it's going to go further up the page, hence the larger angle. And we could answer again in degrees or radians. We could call that pi thirds if we really wanted to, but now it's ultimately just what is the tangent ratio of that angle, or for that one it's the steeper one again, so that should be the larger slope, which is the rad 3 value. So square root of 3 is the value for that one, and notice anytime it says this exactly, like the last couple of examples have had, ultimately what I'm saying is I don't want it in decimal form, I want it to be in some form of either radical or fraction format. So just kind of be aware of anytime it says something about exact, I usually am trying to nudge you in the direction of please don't use a decimal or just type it in the calculator, because the calculator would just give you only a decimal version that you would have to round. So just kind of keep that in mind. You could check your answer using a calculator just by typing it in and seeing if you get the same decimal as if you typed in square root of 3. But that, again, that should be more how you're checking your answer, not how you're finding your answer. Moving on now to number 7. Number 7 just wants us to accurately identify which graph goes with which inverse trig function. So basically all 3 that we talked about in class will be fair game on the review. I just happened to, for whatever reason, choose arc cosine, but arc sine or arc tangent would be fair game. So could be this one, or it could be one of the other two, so just make sure that you're familiar with each one. In case you forget, hopefully you can at least remember what the original function would look like. So cosine's graph, recall, is the one that would start at a high point, then go to zeros after that, and then a low point, then back to a 0. So if I were to just do a really, really rough sketch of what cosine should look like, it should be something like that. And if you recall what's supposed to happen when we have an inverse, inverses are supposed to kind of reflect over this diagonal y equals x line. So if we were to think in terms of what would that look like, well, the result of reflecting that specific function should make what was a y-intercept now be an x-intercept, then what was an x-intercept now be a y-intercept. So this one would create a graph, if I were to reflect it, that would take kind of this portion right here and reflect it across that line, and it would turn into what I just drew there in purple. So which of those out of the 4 options that we got is the one that best matches that? Well, it looks like to me the only option that matches would be C, so I would go with an answer of C. If we wanted to actually just break it down graph by graph, the A value, if you look at that one, that looks like a tangent that's been turned sideways, so that would be the arctangent function. And then the difference between B and D is a little bit tricky, but you got to kind of think in terms of what would the sine graph have looked like initially if I were to reflect it. So if I think in terms of taking that specific graph there, probably don't need any of that over on that side, but if I reflect that over, it should create the graph that goes into the 3rd quadrant and 1st quadrant, not so much the 2nd and 4th. So this one would have been the arc sine. I guess I could write it in the notation you guys have been used to of that. This one would have been the arc tangent. This one was the arc cosine, and then the last one was actually the arc sine that was reflected, so that one really doesn't have a specific name for it. It's just the negative of the arc sine function. But not that that's a worry. Again, it's just be familiar with each of those 3 and just be ready to answer one of those when it comes to, I guess, this specific part of the test. So that wraps up the first standard, which was all the inverse trig, or that was more like the 7.4 section in your homework or notes. Now moving on to the second standard on this test, which is more like the 7.5 section, which was all about solving. So recall with solving, we have to kind of worry about what type of answer to put, whether it's going to be degrees or radians, and then also pay attention to any restrictions on what my solutions can fall between. So like, for example, as you can see with the first 3 problems, it just wants us to only find the solutions between 0 and 2 pi. So that already, right off the bat, is telling us I want to answer in radians. So all 3 of these questions will be answered in radians. But we also have the other thing of trying to approach this where I just want to figure out how do I get the trig by itself, and if I see any coefficients on the x's inside, potentially I might need to go further than 2 pi initially, because when I divide it might bring an angle back in between 0 to 2 pi. So similar to some of the examples hopefully you paid attention to in class or in the notes. But yeah, again, that's the whole point of this video, is to have extra examples with descriptions, so we may as well jump on in for this one. So number 8, as you can see, the first step we're going to want to do is try and find a way to get the sine all by itself. So to me, it seems logical to go ahead and add the square root of 3 over to the other side first. That would now give me 2 sine of x is equal to that square root of 3. And then the next step would be divide the 2 off, and that now has isolated the sine of x, where now I have sine of x is equivalent to the square root of 3 over a 2. So now it becomes a more reference to the unit circles. So since sine is a y value, I just need to think which one has a pretty large y value. So I'd be further up on the y-axis, so that should be these angles that are a little bit steeper in the first and second quadrant. So if we think about what would this angle be and what would the other bigger angle be, it does need to again be in radians. Those should be the pi thirds, or the ones with 3's in the denominator. So the first one actually is pi thirds, the second one actually is 2 pi thirds. And those would be the only 2 places between 0 and 2 pi that would give us a positive rad 3 over 2, because in the other 2 quadrants, those actually would be negative y values. So I only had to worry about the top 2, and usually these do happen in pairs, just as kind of a forewarning with that, unless you introduce a square root, where then a plus or minus would get involved. That might have 4 solutions, but generally speaking, you should kind of go into each of these that I'm probably going to have at least 2 angles from the unit circle that should match the ratio that's being asked, or the one that we're trying to find. Number 9, as you can see here, has a little bit of a change to it. I actually have, instead of just an x on the inside, I have a 2x on the inside. So if you recall the notes or example that we worked through in class, that just means I'm basically going to need to go an extra time around the unit circle, so go 2 rotations around, because in the end eventually I'm going to have 2x equal to the list of angles, and then I'll have to divide them all by 2. So that's just kind of foreshadowing for what we should expect to see when it comes to working through this problem. But first I'm going to go ahead and just try and isolate the tangent so I can get the tangent out of the way. So starting with adding the square root of 3 over to the other side makes the most sense. That then gives us an expression of tangent of 2x being equal to the square root of 3. And now again we just reference what angles on the unit circle would do that. Well, tangent again was like slope, square root of 3, that should be a positive slope, so that should be a line that comes up the page, and it really should be the steeper of the 3 options. Remember, the ones in the middle are 1s or negative 1s, and the ones that are closer to the x-axis are more square root of 3 over 3, so it would be one of these steeper lines. Had that had a negative sign, it would have been just steeper in the negative direction. So anyway, I now can see my 2 original angles. Again, this needs to be in radians from the instructions here. So I need to picture each one of those, but instead of setting it equal to x, I'm going to set it equal to 2x, and it looks like my first one would be at pi thirds, the second one would be down in the third quadrant, which is 4 pi thirds, but then I need to think of 1 extra rotation because of that 2, so if I go ahead and go 1 extra time around, I'm just going to add 2 pi to this. In this scenario, the 2 pi I can really picture like it's 6 pi thirds, and I'll end up doing the same thing for the next one after 4 pi. So if I did 6 plus 1, that takes me up to 7, so 7 pi thirds would be the next one. And then 6 plus 4, that would take me up to 10, so 10 pi thirds would be the one after that. And I could technically keep going and going and going, but because it was only a 2, I only have to really do that second rotation, which I've technically accomplished by adding 2 pi to each of the original angles. So now, of course, we would now try and isolate the x, so I would divide everything by 2. And if you remember how we can divide fractions by 2, if the number on top is even, I just cut it in half. If the number on top is odd, then I just double the denominator. So like this first one, a 1 pi over 3, 1 is an odd number, so I can't really cut it in half very nice. So if I just go ahead and double the bottom number, I'd end up with that becoming pi 6. The next one, 4 pi thirds, cutting that in half, actually that's an even number, so I can do that relatively easy. That's actually 2 pi thirds. Next one, 7 pi thirds, cut in half. 7's an odd number again, so that's going to actually stay 7 pi on top. And turn the denominator into 6 times 2, which would be 3 times 2, which would be 6 if I could speak. And then the last one, again, 10 pi thirds, cut in half. I can cut 5 or 10 in half into a 5. And then have the 3 stay in the denominator. And again, that if I went to the next rotation, it technically would be a value that's larger than 2 pi. In this case, the 2 pi I would probably need to worry about is in terms of 6, so as long as it's less than 12 pi 6, I would keep listing these out, but the next 2, if I did have them, would come back larger than 2 pi, so I've technically listed all 4 that I could find that would satisfy this specific problem. Number 10, just the only difficulty we have with this one is we're going to have to deal with the power of 2, so kind of foreshadowing again. Expect at some point we're going to need to introduce a square root, and if we introduce that square root, we need to remember the plus or minus symbol. So our first goal, though, is to basically just get the trig part by itself. So the way that we could accomplish that is adding 1 first. That would now give me 4 sine squared of x is equal to 1. And then divide the 4 over. And notice that would now give us a new expression of sine squared of x being equivalent to 1/4. And then the last step would be to introduce a square root. And with that square root, I'll put the plus or minus symbol, so that now has gotten rid of the power of 2, so I now have just sine of x on the left. And let's go ahead and square root the fraction. I know it's going to keep the plus or minus, so I may as well keep that. But square root of 1 on top would stay 1, square root of 4 on the bottom is 2. So this is just going to be when is the sine ratio equal to 1/2. So if we think about what sine is again, sine is the y value. I know it's going to be not very high up or not very low down because I have both the positives and the negatives, so it's going to be the angles that are a little bit flatter in each quadrant, or the ones that are kind of closer to the x-axis. And if you recall, all of those should be the ones that are pi 6. So with this one, all of those values are going to start with pi over a 6 in some way, shape, or form. It's just a matter of what's the coefficient on pi. Well, in the first quadrant, it would just be 1 pi. Second quadrant, it would be 5 pi 6. Next one in the third quadrant, now that I have the negative 1/2, so that would be 7 pi 6. And in the fourth quadrant, again, it's a pi over 6, but this one, it's getting closer to 2 pi, so that must be 11 pi 6. And I'll go ahead and just transfer those up onto this. Probably should have done that to begin, but just wanted to make sure that we had the process here down of we're just identifying where that ratio happens on the unit circle and taking advantage of what those values would be. Again, why did I answer in radians, not degrees? That had more to do with just the instruction set at the very beginning. Remember 8 through 10, it said 0 to 2 pi, which I've been able to go ahead and find. Moving on now to number 11, notice the instructions here have changed a little bit. Now I actually get to answer in degrees. Still is just go one rotation around, so it's just one time through the unit circle. This one, though, what also is complicating things a little bit is now not only do I have the power of 2, but I also have a linear term over here, so this seems more like it's going to be a quadratic approach, so I'm going to go ahead and just move everything to one side and go ahead and get 0 somewhere. So with this one, if I go ahead and move everything to the left, that keeps at least my square term positive, hence why I wanted to do that. And the way I would move both of those is with subtraction, so I'm going to go ahead and subtract 5 sine of x here in the middle, and then subtract 3 at the end, and now I have the 0 on the right side that I was shooting for. So now I just treat this kind of like it's just a quadratic. If it helps, you can think of this as 2x squared minus 5x minus 3 as really the quadratic form that we're going to factor. So remember, to get the ball rolling with these, I multiply the a and c values, which 2 times negative 3 would give me negative 6. I'll now want to multiply to negative 6, but add to the middle coefficient, which is the negative 5. So what pair of numbers would do that? Well, I think it would be a negative 6 and a positive 1. And we can now think like reverse Punnett square. If this was 2x squared and negative 3 on one diagonal, the two numbers I just identified, negative 6x and positive x, would be the ones that combine here along this diagonal to turn into the middle term, negative 5x, if we just kind of think backwards with how a Punnett square works. So with this, now that I have those parts filled in, I just need to figure out what would go on the outsides. So if I just go with this first top row, what goes into both 2x squared and negative 6x? Well, 2 for sure, and it looks like they both have an x, so it would be a 2x, which then to get 2x squared means the top edge had to have an x on it. And if that's x, the bottom left corner to stay x would need to be a positive 1 that I would multiply by. And if it's positive 1 on the left, to make negative 3 on the bottom right, that would need to be a negative 3. So if this were just the quadratic, it would be one factor is x minus 3, the other factor is 2x plus 1. But again, this is not just x's, it actually is sines, right, from right there. So I need to make sure that when I do my factors, I set it up with a little bit larger parentheses, and then let's do the one with a 2 first. So that would be, instead of 2x, it's going to be 2 sine of x plus the 1, and the other one's going to be sine of x minus the 3. At this point, because I've turned what wasn't a product into a product, now if either of these parentheses was 0, the whole thing would be 0. So now I really just set each part equal to 0 and solve. So the first one, it looks like I would just subtract 1 first and then divide by 2 after that. So this is going to be a sine of x equaling negative 1/2. And then now we'll go ahead and maybe picture where that would happen. Well, negative 1/2, those are similar. I think we actually just did that not too long ago. They're going to be the ones closer to the x-axis, so that looks like to me in degree format, that's going to be, what is that, 30 more than that, so 210 degrees, and then 30 less than that, so 330 degrees. My second part, if I go ahead and try and solve it, it would be when is sine of x minus 3 equal to 0. I'd add the 3 over. I hope we recognize at this point that the largest value I can actually get for sine is 1. 3 is too large. That actually is not a ratio that happens on the unit circle anywhere. So technically there aren't any parts that would make that second parenthesis equal to 0 at all anyway. So I don't have any more solutions. It would just be the two that I've listed up there already, which again just came from the sine of x equaling negative 1/2 portion of these factors when I set it equal to 0. For number 12, this is one where I'll probably want to do a little simplifying to start and try and figure out what maybe I can come up with. This one again still is going to answer in degrees, so just 0 to 360. and just try and think in terms of what do we actually have. So how could this actually turn into something that can simplify? First off, I'd probably want to try and replace the cotangent with something it's equivalent to. So sine of x times, and then cotangent is cosine of x over sine of x. And I just want to figure out when does that equal square root of 3 over a 2. So for this specific example, notice we can see that there's a sine of x that will reduce with that sine of x. And now it's just going to be leaving when is cosine of x equal to square root of 3 over 2. And so now it will just be reference when does that happen on the unit circle. So x is the cosine, so this is going to be a little bit further out. So it seems like it's going to be the two flatter angles in the first and fourth quadrants because I need to be positive. And if I answer in degrees, the first one would just be the smallest angle we got, 30 degrees. And then one of the fourth quadrants, like the last example, is the 330. Maybe you might be thinking, like, what do I do about the sine of x that canceled out? Well, technically, all that has is just a domain restriction, but it still technically is not a part of what would make rad 3 over 2 happen. So even though, yes, it did cancel out, I only needed to really worry about the what was left afterwards and set it equal to whatever the value was on the right, which was the rad 3 over 2. So the sine of x in this problem technically didn't really have any values that would have become a part that could have given us a rad 3 over 2 anyway. Finally, to our last one, number 13 here just wants us to identify, this time it says all solutions, so it's not giving us any sort of restriction. And it also does specifically say radians. So if this says something about all solutions in radians, I hope immediately what popped into your head is I probably need to do something with some 2 pi k's to my answers. So ultimately what I'm going to do is try and, again, solve like usual. Go one time around. I don't see any 2x's or 3x's or anything inside of the trig, so it looks like everything is just a single x. So I just have to go one time around and list out all those angles, and then basically whatever I get, I'll just say plus 2 pi k at the end. So if we look at what we're starting with, it's kind of nice. It's already equal to 0 on the right side. I do have two separate terms, so what it looks like I can do is just take out whatever they have in common. So they do both have a cosine of x, so if I took that out, what would that leave on the first term? Well, it should leave the sine of x, and then from the second term, it should just leave the coefficient, because it would be technically a 1/2 that's multiplying with a 1. And then the subtraction in between just stays subtraction. And all of that still is equal to 0 because of what was on the right side, and now, because I've turned it into a product, I should be able to just separate it and say if cosine of x was equal to 0, the whole thing would 0 out. And the second one is if sine of x equaled, go ahead and add the 1/2 over, equaled positive 1/2, the whole thing would be 0 as well. So now if we think in terms of where do these things actually happen on the unit circle, for this one, cosine is 0 when the x is 0, so that should be the 2 points that are on the y-axis. So in terms of radians, that technically would start with a pi halves for the first one, and the one at the bottom is going to be a 3 pi halves. So I'll just use the first two blanks with each of those, and I'm going to go ahead and just add on the plus 2 pi k's right now while I'm thinking about it. As for this second solution, when is sine equal to 1/2? Well, that's a y value again. So it seems like I wasn't very, I guess, creative with the selecting of these equations. I keep getting a lot of these 30-degree, or in this case, the pi 6th angle that keeps happening here. So again, those are the smaller ones. This is pi 6 in the first quadrant. I'll go ahead and put the plus 2 pi k for all rotations around from there as well. And then on the second quadrant, that one would actually be the 5 pi 6. And again, plus 2 pi k. And all that 2 pi k is doing is just saying if I go full rotations around, if I start at that angle and go all the way around, technically that won't be in a new spot. So the ratio for either a sine or a cosine, whichever function we're trying to zero out, would technically be the exact same because, well, I haven't changed the position. So my 4 solutions for this one, that technically is a list of infinitely many solutions, which is kind of tricky to think about, but that's essentially what this 2 pi k is doing, is it's listing out everything without me actually having to physically list them out. So anyway, hopefully this video has been helpful in at least giving you an approach for each type of problem, but if you have other examples or you just have follow-up questions that you need to have addressed, come find me and we can work through some extras, or hopefully I can provide a different description that would help make it make sense. So anyway, I appreciate you taking the time watching this video if you've made it this far, and we'll go ahead and catch you next time.